Let's go ahead and do our usual thing. Let's do a quick sound check. And sound looks fine, and can I see my hand? Okay, and the camera is working just fine. Alright, let me go ahead and put away these headphones then. And let's figure out what we're going to do today, because I still haven't figured that out yet. Might want to grab this book. Oh boy. So, I'm not entirely sure what it is I want to do today. I have a variety of ideas in my head, and I'm still kind of undecided, but I think I'm just going to default to continuing with electromagnetism. I don't have nearly as much stuff done for electromagnetism as I have for mechanics, so I think I might as well continue with that. Let's see what we can do for today. So I've been doing Gauss's law, doing electric fields and all that, and once we have electric fields, we can calculate electric potentials. So that's probably where I want to go for today. And then this is just... I mean, I guess we could also do electric potential energy since it's a related concept. Decisions. Okay, let's go ahead and do this problem first. So I'll go ahead and write down the formula for electric potential, or rather, change in electric potential. Change in electric potential is equal to the negative of the integral of the electric field with respect to position. Negative integral of E dot dl. Usually our dl is just going to turn into an equivalent dr, and a lot of the steps are going to be similar to what we did last time and the time before that, which is just identify your electric field in the different regions of interest around your setup, and then after that, take whatever electric fields you have, and for each interval, take the integral. Let's go ahead and look at problem 1 in my book, which gives us a concentric spherical insulator and conductor. So it says a solid insulating sphere of radius A is fixed at the origin of a coordinate system as shown. The sphere is uniformly charged with a charge density of rho. Concentric with the sphere is an uncharged spherical conducting shell of inner radius B and outer radius C, and it's asking for electric field and electric potential. I'm just going to find the electric potential in all regions of interest. I'm just going to go ahead and find electric potential in all regions of interest. So let's go ahead and draw the thing first. So we have an insulating sphere. inside of a spherical shell. Let's see if I can draw my spherical shells any better than last time. Probably not, but gotta try. How do I want to do this? So I want to draw a circle. And then what I want to do is draw something like this. And then something like that. Maybe I'm putting more effort into this drawing than I should be, but I really want to try and figure out how to do these drawings. And maybe, not promising, but maybe next week, if I can make enough progress learning or reteaching myself how to use Blender, I might actually have some 3D models to show you instead. Of course, that would require me to actually find time to do prep, which I haven't been doing for the past couple weeks, so we'll see. We will see. I guess I drew that pretty well. Only issue is this thing should have been a little bit higher up, which I guess actually means I should have drawn the bigger sphere just a couple millimeters lower, but I think that's progress. So we have a spherical shell. Let's see. We have a spherical shell with inner radius B and outer radius C. That's going to be B, and that's going to be C. And then the radius of the insulator is equal to A. And they tell us that the inner sphere has a uniform charge density rho, what else do they give us? And they tell us that the outer sphere is conducting and uncharged. Conducting and uncharged. That doesn't mean there's no charge on either of its surfaces. All it means is that the total charge on it is 0. I misspelled it. Great. Uncharged. All right. Regions of interest are actually, I don't need the arrowhead, just the magnitude of the electric field as a function of R is from R between 0 and A, R between A and B, R between B and C, and R greater than C. Those are our regions of interest for which we want to determine the electric field using Gauss's law. Okay, so first up is applying Gauss's law for a Gaussian sphere of radius smaller than that of the inner sphere. We know that the electric field on all points on the surface of that sphere are going to be pointing outward. parallel to the surface normals of our Gaussian sphere. So E dot dA simplifies to E times dA, as we've seen last week and the week before, for those of you who actually watched those recordings. And that equals the total charge enclosed over epsilon naught. Nothing fancy with the E dot dA, it becomes E times dA. The E is a constant that can be pulled out, and the integral of dA is just the surface area of our surface, which in this case is a sphere, so 4 pi r squared. And then the hard part, of course, is the charge enclosed. So let's see. For our charge enclosed, the amount of charge enclosed within a Gaussian sphere of charge density rho, that's a volume charge density, that's going to be given in coulombs per cubic meter. So to figure out how many coulombs of charge we have in there, we multiply by the number of cubic meters. So let's see, that's going to be Q enclosed equals rho times volume enclosed. Notice, by the way, I should mention this now, that the V for volume I write without serifs. V for voltage I write with serifs. That's just my way of keeping the two separate from each other, because using two things that are symbolized with capital V can get quite confusing. Let me actually make those serifs a little bit more obvious. There you go. So yeah, I will try to represent my voltage with serifs in order to keep it separate from volume. Anyway, where was I? So, volume charge density multiplied by volume enclosed. If the radius of my Gaussian sphere is r, such that r is between 0 and a, then all I have to do is multiply rho by the volume of that sphere. So we are going to have rho times 4/3 pi r cubed. So we can go ahead and plug that in there and see what that gives us. I can already see the pi's are going to cancel out at the very least, and the 4's, and 2 of the r's. We've got E times 4 pi r squared equals rho 4/3 pi r cubed over epsilon naught. Pi's cancel out, r squared reduces with r cubed, leaving just an r over there. The 4's cancel out, and we have electric field is equal to 1/3 epsilon naught times r. If you remember from last time and the time before, I like to try and move my variable term and put it outside separately. Can be helpful in cases where you get asked to draw the graph. At least you can have the constants separated out so you can immediately tell from the variables what kind of graph you're looking at. In this case, if I've got constants times just the variable to the first power, that is going to be a linear graph. So the electric field strength varies linearly with distance from the center, as long as you're within the insulating sphere. Okay, next up, I want to do a region of space that is between A and B. So basically, that if I draw that Gaussian sphere, then the total charge enclosed, it's going to be the same. The left-hand side is going to be the same. It's going to integrate to e times 4 pi r squared. But the right-hand side is going to be different because the charge enclosed is now just going to be the total charge of the insulating sphere. So I'm going to just go ahead and copy down pretty much this stuff right here. I'll do it starting up here. So we've got e times 4 pi r squared is going to equal, the charge enclosed this time is the volume charge density times not the volume enclosed, because not all of the enclosed volume has charge in it, right? This stuff over here, empty. All the charge is just up to this point. So I'm just going to do volume of the insulator itself, the total volume of the insulator, over epsilon naught, and the total volume of the insulator, since it has a radius of a, that must be 4/3 pi a cubed. It is a constant, so we've got e times 4 pi r squared is equal to rho times 4/3 pi a cubed all over epsilon naught. The 4 pi cancels out, and that's the only thing that cancels out this time. Divide the r squared over to the right hand side, and I get e equals, let's see, oh, come to think of it, I just realized I forgot something. I forgot the rho. It's not 1 over 3 epsilon naught, it's rho over 3 epsilon naught times r. I just realized that. Just goes to show that no matter how many years you spend doing physics, you're still going to make mistakes. Same for math. So, yeah, you're never going to get to a point where you can't make mistakes, is what I always tell my students. You'll only get to a point where you get better at catching them. Anyway, dividing by r squared, I would have rho and a cubed, and then the 3 and the epsilon naught at the bottom, so rho times a cubed, and then 3 epsilon naught, and then I'm going to have 1 over r squared times 1 over r squared. Okay, so rho a cubed over 3 epsilon naught, all that stuff is constant, and then times 1 over r squared. That's for our second region of interest. Third region of interest is easy. Our third region of interest is going to be right here, where r is between b and c. So if you draw a Gaussian sphere of radius between b and c, we see that it has its surface right inside of the conductor, right within the bulk of the conductor. So we already know what the electric field within the bulk of a conductor must be. It is 0. It has to be 0 unless, if you remember from the session we did 2 weeks ago, unless there's some sort of external electric field that's so strong that there aren't enough electrons within the conductor to rearrange in such a way as to counter it, the electric field within the bulk of a conductor is always 0. And then finally, if we look outside of the conductor, if I draw a Gaussian sphere that surrounds the whole entire setup, then Gauss's law gives us E times 4 pi r squared for the left-hand side. And for the right-hand side, we're going to have total charge enclosed over epsilon naught. But wait a minute, the total charge on the conducting sphere is 0. So you get nothing from the conducting sphere. All the charge you get is the charge of the insulating sphere, and we already know what that is. That's rho, well, it's not rho times a cubed. You would do some cancellations. But the point is, well, I guess I could just say this. It's rho times 4/3 pi a cubed. And then if you cancel the 4 and the pi again, then you just get this result again. You just end up getting this result yet again, except this time the values of r are greater than c. So we just get rho a cubed over 3 epsilon naught times 1 over r squared. And I could ask a bonus question here. What is the total charge on the inner surface versus the outer surface of my conductor? If the electric field at r between B and C is supposed to be 0, then that would mean that the charge enclosed would have to be 0 for this region, which means the charge on the inner surface of the sphere plus the charge of the inner sphere, the charge on the inner surface of the conductor plus the charge on the insulator has to be 0, which would then mean that the charge on the inner surface of the sphere is... what color should I pick? I think the pink one was dying last time. Does pink still work? Yeah, it still works. The charge on the inner surface of the conductor would have to be, I'll call it Q inner, has to be equal to negative Q insulator, which equals negative rho times 4/3 pi a cubed. And if I asked you instead for the surface charge density on the inner surface of the conductor, then you would just take this and divide it by the total surface area. So I would do, oh, and did I copy my, yeah, I did copy the negative sign for a minute there. I thought I didn't. I could say sigma inner is equal to, let's see, it would be negative rho times 4/3 pi a cubed. Oh, I can already see it fading. We might have to just trash this pink marker, or Sharpie, I guess, if you want to be technical about your terminology here. Anyway, total charge, negative rho 4/3 pi a cubed divided by total surface area, which would be 4 pi, and then the inner radius is b, so 4 pi b squared, and you can cancel the 4 and the pi, and you can get the surface charge density for the inner sphere. We can then follow a similar process to get the surface charge density of the outer sphere. It will basically just be, let's see, since the total charge on the conductor is 0, whatever charge is on the inner surface, the opposite charge must be on the outer surface. So Q outer, I guess I'll write it up here, Q outer is equal to negative Q inner, because they have to add up to 0. And negative Q inner is just Q of the insulator, which is rho times 4/3 pi a cubed without the negative sign. And then divide that by 4 pi c squared in order to get the outer surface charge density, and you're done there. So that's how you would address those two questions about total charge on the inner and outer surfaces and the surface charge density. Anyway, we want to now take this and move on and determine the voltage, the electric potential at all of these different places. So when doing electric potential, I like to work in the opposite direction. Instead of going from the inside out, like I did when coming up with all of these, for electric potential, I like to work from the outside in, for reasons that will hopefully become apparent in a minute. So to get electric potential, because this integral doesn't give you electric potential, it gives you change in electric potential. So you have to pick a starting point as a reference and integrate from that starting point. And 0 is not a very good starting point to integrate from. 0 is usually not a good starting point. Instead, our typical starting point is going to be just at infinity. So I'm going to do, let's see, I guess I'm going to copy over what I have here, and then I'm going to go ahead and write down my my voltage function. So E of R is equal to, let's see, we had rho over 3 epsilon naught times R for the first region, and then rho a cubed over 3 epsilon naught times 1 over r squared for our second region, and 0 for our third, and then rho a cubed over 3 epsilon naught times 1 over r squared again for our last region, r greater than c. B and C. Okay, barely squeezed it in there, but there we go. I know my braces are uneven. I'm sure I'm driving people with OCD crazy right now, but forgive me. It's not like I was able... Well, I wasn't able to plan ahead for how big this one was going to be, but I could have... Okay, I'll try to do better next time and make it look more symmetric. But that's not a promise. Anyway, now I want to get my voltage function. So I'm going to define V of infinity as being 0. V of infinity I'm going to define as my 0, because the only thing I can actually calculate with this integral is differences in voltage. There is no absolute voltage. Voltage is relative, and it's relative for the same reason that potential energy is relative. Voltage is just potential energy per unit charge. If it depends on potential energy, then it makes sense, since there is no true absolute potential energy, there is no true absolute voltage either. Anyway, let's go ahead and make some room for this. I'm going to try and make it just as big as this one, because actually it's probably going to need to be even bigger than that, but we'll see. I won't close this curly brace just yet. So I want to start from the very end, and I want to do delta V, I guess, how do I want to say this? From C to infinity, or actually, wait. No, it would be from infinity to C. Let me think. Well, okay, let me write it this way instead. So I'm going to say delta V is equal to V infinity minus VC is equal to, and then it's negative integral E dot dl which simply reduces to E times dl if you consider the fact that our electric field is going to be outward, right, in this region. If you assume that the charge density of the insulating sphere is positive, then the electric field from it is going to be radially outward. And the direction in which we're integrating, if we're coming from some point infinitely far away and moving towards the surface, then we're moving radially inward. So radially outward and radially inward, those are anti-parallel vectors. So it would just become E times dl times negative 1. And our dl, of course, is equivalent to dr. If L is just position starting from this point and moving. Actually, wait, no. L would be position starting from the center and going outward, because L would be 0 at the center of this system. So L, basically what I'm trying to say here is that dl is equal to dr, because small changes in L and small changes in R are equal to each other. I know there's a better way to phrase that, but it's not coming to mind right now. But you've probably seen this enough times in your class to understand what I'm getting at anyway, even if I'm struggling to put it into words right now. Let's see. So E times, so we're going to get negative integral of, well, E for R greater than C is going to be rho A cubed over 3 epsilon naught, rho A cubed over 3 epsilon naught times 1 over R squared, and then that times dr, and times negative 1. Times negative 1, because, actually, wait, no, it wouldn't be times negative 1, because the way we're defining dl, or dr in this case, the way we're defining r increases from the center and outward, and if we're assuming rho to be a positive charge density, then the electric field is also outward. So actually it would be E times dr times cosine of 0, and cosine of 0 is 1. Okay, yeah. Because I'm looking at it and I know what signs I should be expecting, so that's what's tipping me off that something was wrong with the negative that I introduced earlier. Okay, so we don't actually get a negative from this dot product, we just get a positive 1. And then we are integrating from infinity to, I guess, all the way to c. All of these are constants, so we can pull them out, and that gives me negative rho a cubed over 3 epsilon naught, and then I'm missing something. Oh, it's supposed to be r squared. And then integral from infinity to c of 1 over r squared dr. 1 over r squared can be rewritten as r to the negative 2, which then integrates, let's see, negative rho a cubed over 3 epsilon naught, and then r to the negative 2 becomes r to the negative 1 over negative 1, so negative r to the negative 1, or negative 1 over r. And then from infinity to c, so negative 1 over c minus negative 1 over essentially infinity. I know technically, for you mathematicians out there, technically I'm supposed to call this some constant and then, or some variable, and then take the limit as it approaches infinity, but we're physicists, we don't worry about that, so this is effectively going to be 0, as it should be. We did set v of infinity equal to 0, and then these negatives will cancel out, and I will just be left with rho a cubed over 3 epsilon naught c. So I guess I will just do this and hope that I have enough space. So we would have, actually, come to think of it, I should have integrated from infinity to r with r greater than c. My bad. So just mentally replace this c with an r, and as a function it would be rho a cubed over 3 epsilon naught times 1 over r. And that's for r greater than c. Okay. Then we move further inward to our next region of interest. So if you start from infinity and you work your way closer and closer and closer to the surface of this sphere, you will experience an increase in voltage, right? Because as r gets smaller and smaller, as you get closer and closer, you have smaller and smaller distance from the center. And as you get smaller distance from the center, this thing increases in magnitude, and if we assume rho to be positive, then that would mean that your voltage is increasing as you get closer to the surface of the outer sphere, which does make sense to me, because if you're getting closer to an arrangement of charges that's overall positive, then your voltage should go up. Voltage should be higher as you get closer to positive charges and lower as you get closer to negative charges. So that so far is making sense to me. The signs that I'm getting are all checking out. Maybe that's a bit nitpicky for some of you, but double checking and making sure that the signs you get are making sense can make or break some of these problems. So I would definitely recommend getting in the habit of doing that. Anyway, next region of interest, if I want to do, let's see, if I want to do my next delta V, I guess I'll do it over here. It's not going to be all that impressive. This next delta V is going to be starting from the outer surface of the conducting sphere and working my way towards the inner surface. So delta V is now going to be V, let's see, what's it going to be? V, I'm just realizing I made yet another mistake. This is supposed to be Vc minus V infinity, not the other way around. This is supposed to be Vc minus V infinity. Anyway, so here we're going to V sub B eventually. Actually, I should call it V sub R, and I should call this V sub R as well. And then what I want to do, I don't want to start from infinity. The reason I don't want to start from infinity is because I already know what happens if I integrate from infinity to the surface of my sphere. So instead I want to start from the surface of my outer sphere and work my way towards the inner surface of the outer sphere. So I'm going to compare the difference between voltage at position R, which is any random place between B and C, and voltage at a distance of C from the center. And that's going to be negative integral E dot dl, or I guess E dot dr. And this is actually going to be 0, because electric field in that region for all points where R falls between B and C, the electric field is 0, and the integral of 0 is always 0, so actually we don't have to do anything else. V sub R minus V sub C for all R between B and C is 0, which means then that V sub R in this area is equal to V sub C. If VR minus VC is equal to 0, then VR equals VC. And what is VC? VC is just rho A cubed over 3 epsilon naught times 1 over, not R anymore, but C. Just following this formula and plugging in the value of C for R gives you the voltage once you come from infinity and hit the surface of this outer sphere, and then from there the voltage remains constant until you hit the inner surface of that same sphere. Okay, so that's for R between B and C. All right, now we work our way further inward. So let me see, where do I want to draw this? Or draw, right. You know what I meant. I suppose I can still fit it down here. But, well, actually, I'm going to have the same integral that I did for the outermost region because the electric field takes on the same form. So the only thing that really needs to change is my is this part of the expression, the delta V part. So maybe I can fit it in up here actually. So delta V now is going to be from the inner surface of the outer sphere and then towards the outer surface of the inner sphere. So delta V is going to be V sub r, where r is between A and B now, minus V sub whatever the voltage is at, if we're going to start, we'll start from position B. Well, what's the voltage at B? The voltage at B is going to be equal to the voltage at C because there is no change in the voltage as you move further inward from C to B, right? The voltage is constant for this region. So I already know that V of B is just going to be, where do I want to write this? I guess I'll write it over here. V of B is just equal to rho A cubed over 3 epsilon naught times 1 over C. And then that equals negative integral E dot dr, and we know what the negative integral of E dot dr is going to give us. It's going to give us rho A cubed over 3 epsilon naught times 1 over r equals rho A cubed over 3 epsilon naught times 1 over r, minus, of course, VB. So that's times, so this would have been 1 over r because the integration bounds would have been from B to r, and then wait a minute. That's not right. Is that right? Times 1 over r minus, This doesn't seem right to me. Hold on. If I were to do this integral from starting from point B and moving let me think here for a second. Does that actually add up? Oh, okay, yeah. I'm convinced by it. I'm not entirely sure how to explain it, though, other than to just say, yeah, when you evaluate the integral, this is what the change in voltage is going to be once you start moving from a point on the inner surface of the outer sphere and you start moving towards the inner sphere. That change is going to, I'm not sure how to word this. I guess to give you an intuitive sense of it, this 1 over b part matters because this 1 over b part determines the it determines the outer boundary of where the next region of electric field is creating a change in electric potential, I guess. I'm struggling to find a better way to word this right now. But at the very least, following the calculus, if you substitute in rho a cubed over 3 epsilon naught times 1 over r squared, then once you integrate the 1 over r squared part, you would get a minus 1 over r, and I guess the minuses cancel because of that negative out front. So you would get 1 over upper bound minus 1 over lower bound, and yeah. So just from the calculus alone, if nothing else, that tells you that we're doing something right. So VR then is just going to be, let's see, rho a cubed over 3 epsilon naught minus, or no, times 1 over r minus rho a cubed times 3 epsilon naught over b, and then add VB to that. You know what? I'm just going to keep this expression. I'm not going to distribute. So I'll just leave that part out. So the only other thing I need to do is add VB, and that will give me rho a cubed over 3 epsilon naught times 1 over r minus 1 over b, and then plus, if I add the VB, what is VB? VB is going to be just this. It's just going to be rho a cubed over 3 epsilon naught times 1 over c. I mean, I was expecting it to get messy, but I wasn't expecting it to get this messy. Maybe this is why they don't usually ask you to get the voltage for all regions of interest. I can't wait to see how hideous it gets for this final region. So, if we now move on to our innermost region, if we move, well, first of all, let me determine what is VA, because we're going to need that. VA, so if we moved, let's see, from infinity to the outer surface, and then from the outer surface to the inner surface, and then from the inner surface, if we're now all the way here, and we're starting to drill our way into the insulating sphere. What is the voltage starting here on the outside of the insulating sphere? What is VA, as I'm going to call it? I would just have to plug in A for R in this expression, and let's see what that gives us. That gives us VA equals rho a cubed over 3 epsilon naught times, it'll be 1 over a minus 1 over b, and then plus 1 over c if I factor out the rho a cubed. So rho a cubed over 3 epsilon naught times 1 over a minus 1 over b plus 1 over c. All right, and finally, an integral. Can I fit it all into one page? So I now want to calculate a delta V equal to V of R minus V of A, where R is between 0 and A. Where R is between 0 and A. Equals negative integral E dot dl, negative integral from A to R of E, which is rho over 3 epsilon naught times R. All those constants can be factored out. The only variable here is R, and then times dr. Okay, integral of R is going to be 1/2 R squared, so that's going to give me negative, and then rho over 3 epsilon naught times, it'll be 1/2, and then plug in R, so 1/2 R squared minus 1/2 A squared. Yeah, 1/2 R squared, and then for the upper bound, just plug in R. For the lower bound, plug in A. Okay, yeah, we're good. So this is the difference in voltage. To get V sub R, I would then need to add V sub A to this result. There's my V sub A, so we're going to have, let's see. Oh boy, this is going to be, I don't even know if I have enough room to fit this whole thing in. So it's going to be, I'll do the plus VA first. So I'm going to do rho A cubed over 3 epsilon naught. Actually, since this also has a rho over, oh, actually, no, I can't factor it out. Never mind. Rho A cubed over 3 epsilon naught times 1 over A minus 1 over B plus 1 over C. That should be a minus. I should probably just do a different color so that it's clear. 1 over A minus 1 over B plus 1 over C, that's VA, added to this. So minus, and then rho over, I'm going to factor out the 1/2, so rho over 6 epsilon naught, and then R squared minus A squared. Yeah, very hideous. Usually on a test, they'll only ask you to maybe go this far, and they won't ask you to dig deeper into some of those more inner regions, because yeah, it gets really time consuming and messy, and that time is better spent on asking you other questions about other concepts. So I wouldn't worry too much about it getting this bad on a test, but on homework, this is definitely fair game. And now you know how to do it. Okay, let's have a look at another one. So this one works with cylinders. It says we are dealing with the potential of concentric cylindrical the potential of a concentric cylindrical insulator and a conducting shell, which I assume is a conducting shell. So it says an infinitely long solid insulating cylinder of radius A is positioned with its symmetry axis along the z-axis as shown. I'm not going to worry about how they show their axes. I'll draw my own version of it in a minute. The cylinder is uniformly charged with a charge density of rho. Concentric with the cylinder is a cylindrical conducting shell of inner radius B and outer radius C, not too different from the spherical situation we just finished. It says the conducting shell has a linear charge density of lambda. And then it says what is the electric field at different places and the electric potential and all that. Okay, so I'm going to pretty much treat it the same as I did with this problem. Let's see. So I want to draw, I think I should draw the outer cylinder first this time. Okay, and then that should give it some sense of thickness. Not the best circles I've ever drawn, but they will have to do. And yeah, something like that. Okay, so this time the shell, they said, was a conducting shell with a linear charge density lambda. So we have an insulating cylinder over there. Let me use, I guess I might as well use this fading pink color. This is an insulator with a uniform charge density rho. Uniform charge density of rho. And then this thing is a conductor. Conductor with a total linear charge density of lambda. And then, of course, we have our usual suspects for the radii. We've got A and B. Actually, the way I drew it, that makes it look like the length of the cylinder. Forget this. Let's do this. Call that B. And then do that and call that C. All right. We're going to follow the same steps as before, and if it's anything like the previous problem, then this is going to take up the rest of our time. I'll see if I can try to speed it up now that we've seen a previous example. So, electric field in all regions of interest. Electric field as a function of R, at least magnitude-wise. We've got R between 0 and A. Let me, write that comma a little bit further to the left. And then R between A and B. And then R between B and C. And finally, R greater than C. All right, let's hope that's actually enough space to write in whatever expressions we're going to end up getting from Gauss's law. Let's hope. All right, so first Gaussian surface I want is a Gaussian cylinder that exists within our innermost cylinder. So Gaussian cylinder of radius between 0 and a. So I'm going to do integral E dot dA equals charge enclosed over epsilon naught. And of course, as we've seen before, for a cylinder, first of all, just like with our sphere, this is going to be a perfectly symmetrical situation. The electric field is going to have a fixed magnitude at all points on the surface of our Gaussian cylinder. So we can just pull the E out as a constant. That leaves us with the integral of dA, which is just going to be the surface area of the cylinder, not including the surface area of the bases, because the bases will have no flux going through them if this cylinder is infinite. And if it's not infinite, then usually if the cylinder is long enough, the electric field coming out of the bases is going to be insignificant compared to the electric field coming out of the side surface area. So E times the side surface area of a cylinder, E times 2 pi RL. If you don't remember how we got 2 pi RL, maybe look at, was it the one from last time or the one before that? I'm pretty sure it was the session from last week, where L, of course, is the length of the cylinder. And then that equals Q enclosed over epsilon naught. So figuring out the charge enclosed, we have a volume charge density for our inner cylinder. So I'm going to do rho times the volume enclosed over epsilon naught. And how much volume is enclosed? If the radius of our Gaussian cylinder is r, then the volume of it would be, volume of a cylinder is pi r squared times the height of the cylinder. Since this cylinder is sitting sideways, the height is what we actually called L. So pi r squared L is equal to V enclosed. And yeah, just substitute that in, and we get E times, 2 pi r L equals rho times pi r squared L over epsilon naught. The L's cancel out. One of the R's cancels out. The pi's cancel out. And divide by 2. So we get E equals rho over 2 epsilon naught times r. Rho over 2 epsilon naught times r. All right. Next up, we look further outward. So now we're looking at a Gaussian cylinder of radius between A and B, so something like this. And that would surround all of the charge within the insulator. That would surround all the charge within the insulator. The left-hand side is still going to be the same. We're still going to get E times 2 pi RL for the left-hand side. And for the right-hand side, the charge enclosed is going to be rho times the total volume of the insulating cylinder. So V insulator, and then that's over epsilon naught, and V insulator is going to be pi times A squared times L. So we get E times 2 pi RL equals rho times pi a squared times L all over epsilon naught. The L's cancel, the pi's cancel, and I'm left with E equals, this time I divide by a 2 and an R, so I have rho over 2 epsilon naught, and then times the A squared, and then times 1 over R. And I can see that I did not provide enough vertical spacing here. I can already see this being a problem. Actually, it won't be a problem because the next region is easy. Is there anything else I wanted to comment on for this? Actually, no. Okay, next region of interest. Gaussian cylinder of radius between B and C, so that's going to be a Gaussian cylinder whose surface exists within the bulk of a conductor. We know what that means, at least we should know by this point. It's 0. Total charge enclosed must be 0. And then finally a Gaussian cylinder surrounding the entire setup. And I guess I should actually draw it extending around like that. Okay, how much charge is enclosed now? So we still get E times 2 pi RL for the left-hand side. But now the charge enclosed. So the charge enclosed is going to be Q insulator plus Q of the conductor. And then all that over epsilon naught. Okay, charge from the insulator we just got earlier is rho times pi a squared times L over epsilon naught. So let me actually write this in a different color. E times 2 pi RL equals, for the insulator we have rho times pi a squared L over epsilon naught, and then plus, for the conductor, we're going to have, let's see, for the conductor, we had a linear charge density, so I'm going to go ahead and say lambda times L, and then all that over epsilon naught. Okay, the L's cancel out. I cannot cancel out the pi. I can cancel it from here, but there is no pi over here to cancel with, so actually I'm just going to leave it like that, and I guess I should have just written the whole thing over epsilon naught as is, and divide by 2 pi r. So that gives me, let's see, that gives me rho pi a squared plus lambda all over 2 pi epsilon naught, and also dividing by r, so times 1 over r. And there we go. I could ask the bonus question of determining what the linear charge density is on the inner surface of the conducting cylinder versus the outer surface. But I think we can skip on that just for the interest of time. For the interest of time or in the interest of time? I don't even know what the correct expression is, but that's probably why I'm not the language tutor. You would think that I would be, considering how often I put emphasis on language. I guess those of you who haven't been with me for long enough don't even know what I'm talking about, but I'm just rambling at this point. Okay, let's go ahead and calculate some voltage functions. Let's go ahead and get ourselves some voltage functions. So, again, I'm going to copy these results over. Actually, you know what? Instead of copying them, I can just keep on flipping over to the page. Yeah, it's probably faster that way. So, let's see. Voltage as a function of R. I have no idea how long to make this. I'm going to do the same thing I did with the spherical situation, which is start from outside and work my way in. So, delta V, and I guess I'm going to try and come up with a subscript for this. So I guess it would be delta V. I want to call it delta V from infinity to C. At least that's the notation I'm going to use. I don't know if it actually agrees with the notation used in textbooks. Actually, I don't know what notation this textbook uses at all. Let me double check. I mean, I don't have to follow the textbook's notation, but let me just go ahead and see for the sake of satisfying my own curiosity here. Okay, so they've got delta V and then A arrow to B, and that's integrating from A to... Okay, so I'm following the same notation they are. Okay. But, I mean, why would they calculate it from A to B instead of from B to A? I'm working from the outside in, and they're working from the inside out. I think that's why I didn't like... That's what I didn't like about the notation in the book. Now it's starting to come back to me a little bit. But anyway, where was I? So delta V from infinity to C is going to be V infinity minus, no, other way around, VC minus V infinity. V infinity, of course, we're going to be defining as 0. V at infinity, we're defining as 0, equals negative integral from infinity to C of E dot dl, or in our case, dl is equal to dr. Alright, and E dot dr just becomes E times dr because the direction of the electric field, at least our positive direction of electric field, is going to be outward, and the direction of r is 0 at the center and increases outward as well. So the positive direction of r and the positive direction of E are in agreement with each other. The cosine of the angle between them is 0, so the dot product would just give you times cosine 0, which is 1. So yeah, dot product reduces to a regular product of two scalars, essentially. Okay, plug in for E, starting from the outside, plug in this nasty expression right here, And actually, it's not too bad. All this stuff is constant, so it will factor out of the integral, and all you'll be left with is the integral of 1 over r. So I'm going to do negative, and then all that stuff. So rho pi a squared plus lambda. My goodness. Over 2 pi epsilon naught. And then integral from infinity to c of 1 over r dr. Actually, wait, is this even going to work? I have a feeling this is not going to work nicely, but let's see what happens. In for a penny, in for a pound, I guess. Negative rho pi a squared plus lambda over 2 pi epsilon naught times, this is going to be natural log of c minus natural log of infinity. Oh goodness. This is not going to work. Times natural log of c minus natural log of infinity Okay, maybe choosing infinity as a starting point is not the best idea. What does the book want us to do? Because I guess the other point we could pick is just from the center of the system. Will that give us any problems? So when they ask for voltage, they ask what is Vp minus Vr, the potential difference between points P and R, and P is just some arbitrary point that they drew outside, and they called it P. Okay, and the reason they did that is to avoid this infinity problem. Okay, fine, then we will do that too. Forget about infinity, we will use P. From some point outside of our system of charges. Okay, and this is going to be ln of P. Okay, and then natural log of C minus natural log of P. Using the properties of logarithms, you can simplify this to natural log of C over P. That's about as simple as it gets. So for our outermost region, we've got negative rho pi a squared plus lambda over 2 pi epsilon naught times the natural log of, and come to think of it, I should call this R and not C. I made the same mistake as last time. It's natural log of R over P. And that's for R greater than C. So I guess that's another correction I have to make. That's supposed to be R, that's supposed to be R, R. Little r, not big R. Great, I'm making mistakes left and right. Little r, little r, little r. Maybe I should start doing this in pencil instead. And that should be R. Okay. 0. Well, we remember from last time what happens when you have 0 electric field. The voltage doesn't change. So we start at point P, the voltage starts increasing, assuming that lambda is positive at least. If lambda is negative, then it decreases. Either way, voltage starts changing as you get closer and closer to the outer surface. Once you hit C, the voltage becomes this, just with a C replacing the R. And then after you hit the surface, if you go deeper from there until you reach the inner surface of the conductor, then you're not going to experience any change in voltage. Integral of 0.dr, the delta V is just going to be 0, which means the V is constant from when you reach the outer surface until you hit the inner surface. So that's just going to be negative rho pi a squared plus lambda over 2 pi epsilon naught times ln of C over P, constant for R between B and C. All right, and then we get to this region next. So for this region, I'm going to have I'm going to start with this voltage, and I'm going to do an integral from, looks like B to R, where R is less than B but greater than A. So started here, moved to here, moved through here, and now I'm moving through here. So somewhere along the way in here, I want to calculate the change in voltage from when I left the inner surface of the conductor to some random point before hitting the insulator. Okay, that's going to be delta V from position B to position R is going to be voltage at R. Wait, is that right? Yeah, voltage at R minus voltage at B. Lowercase b, I don't know why I used a capital B there. Okay, and that's going to equal negative integral of E times dr for that region, and that's going to be from B to R. Let's see, V of B, I can write over here to the side, is just going to be, well, this. You know what? I don't want to write it again. It's too long of an expression. Yeah, I think I'm going to skip on writing it. I'm just going to hope that you guys following along will know where V of B comes from when the time comes for me to actually write it in. Integral of E dr. In this case, E is equal to rho a squared over 2 epsilon naught times 1 over r. All that stuff is constant and can be factored out of the integral. So I have equals negative rho, I've already forgotten, a squared over 2 epsilon naught. Rho a squared over 2 epsilon naught, and then integral from B to R of 1 over r dr. That's going to be natural log again, so we get negative rho a squared over 2 epsilon naught natural log of r over b. Okay, and then that, add VB to it, and that gives you VR. So VR is going to be, let me switch to, how about orange? So VB is going to equal negative rho pi a squared plus lambda over 2 pi epsilon naught. You think this is torture for you? It's torture for me too. Times natural log of c over p, and then that is added to this, so minus rho a squared over 2 epsilon naught natural log of r over b, and that's for r between a and b. Oh boy. And then we have one more, and I don't think we'll have any time for anything else by the end of this one. For our last one, for our last region of interest, I want to calculate delta V between between r equals a to some other r value less than a but greater than 0. So that's going to be v new r minus VA. VA is just going to be this expression plugging in a for r, so pretty much it'll be just this with natural log of a over b instead of r over b, so we'll add that in later. Actually, you know what? I'm gonna write it here. VA equals, and then oh goodness, how do I even fit this in? I can factor out a negative and a rho and a 2 and an epsilon naught, and I suppose if I'm taking the difference of natural logs, then I can, wait, can I factor out? No, I can't do that because they've got all this other stuff in front of them. Okay, so VA is just going to equal, I don't even have enough room here, negative rho over 2 epsilon naught times, oh wait, no, I can't even factor out the rho because, you know what, I'm gonna wait until the very end to actually write it down. Or I'm just gonna write plus VA and call that the end of it. Let's see, we had, where were we? We were doing this, so we do equals negative integral e dot dr, which just reduces to e times dr, and then that's from a to r, and what was it? It's rho over 2 epsilon naught r, the easiest integral yet. Equals, and then I'm going to switch colors here because I don't want this all to get blurred together. I haven't used yellow in a while. Rho over 2 epsilon naught r, so negative rho over 2 epsilon naught, and then integral of r dr from a to r. Integral of r is just going to be 1/2 r squared, so we get negative rho over 2 epsilon naught times 1/2 r squared minus 1/2 a squared. And I guess we can factor out the 1/2, and then this would become rho over 4 epsilon naught. And I think I'll just leave the rest as it is. So we would have negative rho over 2 epsilon naught times 1/2 r squared minus 1/2 a squared. I guess it would have been easier to just factor out the 1/2 like I said a couple seconds ago, but oh well. We're already committed, and then that's your delta v from a to r. If we want v of r, we need to add v of a, so watch this. Done. And again, if you want to actually write out what v of a is, copy all of this and replace that r with an a. So that last term would be ln of a over b. Yeah, I'm not going to bother writing all that mess. And that's going to be for r between 0 and a. Would be easier if I opted to just use the numbers that were given in the problem, but I think it's better to do it this way because it helps you practice your algebra more. What on earth am I going to do with the remaining 18 minutes? What can be done in just 18 minutes? Well, actually, this last one might be quick enough to do in 18 minutes. We've done spheres, we've done cylinders, you know what's next, slabs and sheets. Okay, let's see what we have here. So we've got potential of infinite sheets of charge and a conducting slab. An infinite sheet of charge is located in the yz plane at x equals 0 and has uniform charge density sigma 1. Another infinite sheet of charge with uniform charge density sigma 2 is located at another x position. And an uncharged infinite conducting slab is placed halfway in between these sheets. What is the electric field in each region? And eventually they're going to ask for voltage relative to a point P that they've labeled, which makes sense because for slab and sheet symmetry, using infinity is going to give us problems, kind of like what the cylindrical symmetry did for us. I forgot that it wasn't only the sheet symmetries that give you problems with infinity, which is probably why the previous problem took a little bit longer than it should have. Could have avoided a number of mistakes if I had remembered that. But hey, that's part of the reason that I'm trying to focus more on electricity and magnetism during these sessions, because I don't get requested to help with it very often, so I've gotten kind of rusty and I'm trying to stay relevant. Okay, so they drew an infinite sheet of charge like this, and then they have an infinite slab of charge, And then they have another infinite sheet of charge. And then they have another infinite sheet of charge. And I guess my drawing doesn't do it justice, but the slab, it said, was supposed to be halfway between these two sheets. And then they've labeled these positions. So you've got your x-axis running through here. And they've labeled these positions as x equals 0, and then A, B, and C. What else did they say? And then they want us to calculate the electric field relative to actually a number of points. Actually, they gave us a number of points. So they gave us the point P. They gave us the point P, which is right here. They gave us point R, which is over here. They gave us point S, which is right here. And they gave us the point T, which is right there. Let's see what they asked. So they asked, what is the potential difference between points R and P? I can already tell that's 0. If that's not apparent to you, don't worry, we will work it out. And then they want between S and P, and then they want the potential difference between... Oh, and that's it. They don't ask about the potential at T. They ask about the electric field at T, but that's it. Okay, you might remember from last time. If you don't remember, then you can go and rewatch the recording from last week. You might remember that for an infinite sheet of charge, if it has a charge density of sigma on it, so that's sigma 1, that's sigma 2, and then this thing has a sigma total of 0. This thing is going to have a sigma total equals 0. You might remember for an infinite sheet of charge with surface charge density sigma that the electric field is just going to be perpendicular to that sheet, and it's going to have a magnitude of sigma over 2 epsilon naught. Let me take a look. So sigma 1 is positive, sigma 2 is negative, so I'll go ahead and mark this as a positive sheet and this is a negative sheet. And I'm going to have, I guess I'll draw, so the electric fields due to sigma 1, I will draw those in pink. So that's going to be to the right this way, to the left this way. To the right in this region, to the right in this region, to the right in this region. Anywhere to the right of the sheet for a positively charged sheet, electric field is just going to point to the right, and anywhere to the left of it, it's going to point to the left. Positively charged sheets will have electric fields that point outward, perpendicular, and away from your sheet. The opposite is true for negatively charged sheets. So for our negatively charged sheet, let me use this navy blue color, I think it is. It's a very dark Yeah, I would say navy blue. It probably looks black to most people just through the screen. But for this thing, it's going to have electric fields that point inward. So basically that. And then for the infinite slab of charge, I can see that since it's already got two electric fields pointing to the right on it, and I know the electric field in the center, in the bulk of the slab, has to be 0, the charge on the slab has to redistribute in such a way that it exerts a leftward electric field to cancel both of these. So that would suggest that we get a negative charge on this side of it and a positive charge on that side. And because the total has to be 0, I would say that, well, I guess since this side is at x equals b, I'm going to call it positive sigma b. And since this side is at x equals a, I'm going to call that a negative sigma a. And sigma a is going to equal the negative of sigma b. Or if you prefer, magnitude of sigma a equals magnitude of sigma b. But if we do that, then we will get essentially two electric fields in here. One from sigma b pointing to the left, and an equal one from sigma a also pointing to the left, that cancel out these two electric fields. And then let's see. What else? What other effects do I need to take into account? I should probably use different colors for sigma b and sigma a. Oh god. And here I thought this was going to be a quick one. Okay, this might be messier than I first thought. Let's see. So I'm going to use, I'll just use orange to represent, I guess that will be sigma b. I'll represent with orange. So sigma b is positive. It's going to point left within the bulk of the conducting slab, and left here, and left here, and right over here, and right over here. So that is sigma b. For sigma a, I'll continue with this burgundy color. So sigma a is left on the inside of the conductor, right over here, and right over here, and left over here, and left over there. And I think this time I'm going to adopt the other convention I was talking about last week, which is just a magnitude-only approach. So I'm going to say whatever sigma a is, the magnitude of sigma a equals the magnitude of sigma b. And what else can I say? How do they relate to sigma 1 and sigma 2? Well, we're going to have two electric fields, one proportional to sigma a and one proportional to sigma b, which I'm struggling to find the words for this, but okay, let me do this. So EA has a magnitude of sigma A over epsilon naught. EB has, or over 2 epsilon naught, I should say. EB, similar, is sigma B over 2 epsilon naught. And then E1, because this is sigma 1, E1 equals absolute value of sigma 1 over 2 epsilon naught, and E2 equals absolute value of sigma 2 over 2 epsilon naught. Okay, now to express the total electric field in each of these regions, and actually I only need to find it in this region and this region, and I guess this region if we want to ask about the potential at T. And I guess in this region because I want to show how these are related to each other. Maybe we'll do all of them after all. Well, first let me start off by relating EA and EB to E1 and E2. Over here, they need to add up to 0. So I've got E1 is shown in pink. It's to the right. And E2, shown in navy blue, is also to the right, minus the magnitude of EA and EB are both to the left. So essentially, I have E1 plus E2 minus EA and also minus EB is equal to 0. In other words, sigma 1 plus sigma 2 minus sigma A minus sigma B, or the magnitudes of, is equal to 0. So I can also say that the magnitudes of sigma 1 and sigma 2 have a sum equal to the magnitudes of sigma A and sigma B. And if you actually know the numbers to plug in, you can determine the actual values of each of these relative to each other. Well, sigma A and sigma B have the same magnitude, so actually I could just replace this with 2 absolute value of sigma A or 2 absolute value of sigma B. And that would actually give you the magnitude of sigma A equals the magnitude of sigma B equals 1/2 of this sum. 1/2 of magnitude of sigma 1 plus magnitude of sigma 2. So that's for just the sake of the math. Now then, for voltage. So they gave us the point P as our starting point, and they want us to calculate the change in potential from P to R. So delta V from P to R is equal to V of R minus V of P equals negative integral of E dot dl. The electric field in this region of space, looks like it's overall going to be to the right. At least judging by the fact that I've got 3 electric fields pointing to the right versus 1 to the left. It could very well be the case that the electric field pointing to the left is much stronger and strong enough to overcome all 3 of these, but if I were a betting man, I would place my bets on the net electric field being to the right. Either way, whether it's right or left, your dl is from P to R. You're integrating in this direction, straight down. So the dot product of your dl and your electric field, which is either to the right or to the left, is gonna give you E times dl times cosine of 90 degrees, which is 0. And yeah, that's how I immediately knew change in voltage between these positions is going to be 0, because this movement, you're not moving with or against an electric field. If you don't move with or against an electric field, then you can neither lose nor gain any electric potential energy, which means you can't lose or gain any voltage. Okay, next up was calculate the potential difference from P to S. Well, we can just calculate the difference from R to S, because we know that the voltage at R is equal to the voltage at P. Starting from R and going to S, I guess I drew the R a little too low, but it should have been at the same height. Yeah, that's where point R should have been the whole time. We can just do it from R to S, because then we don't have to, mess with angles and twist and turn ourselves into a pretzel trying to work with an angle that ultimately is not going to make a difference. So I'm just going to do it from R to S, and if we do that, then let's see, what would we be doing? We would have to do 3 separate integrals. I'm not going to actually do them because we're kind of out of time here, but I will describe the process. Essentially, you would do the integral from here to here, which is just calculate whatever this net electric field is from these 3 rightward fields minus this one to the left. Whatever that net electric field is, multiply it by this distance, because that's what the integral of E dot dl will give you when your electric field lines only point in horizontal directions, either to the right or to the left. It's just going to be the net electric field times the distance. Then add nothing here, because the electric field inside the bulk of the conductor is 0, so the change in voltage will be 0, which means whatever voltage, whether it's a gain or a decrease in voltage as you move from R to, I guess, A, whatever voltage you get here, that stays constant as you move through the slab, and then when you exit the slab, you start adding or subtracting voltage again, depending on whatever the net electric field is due to these. So again, you're going to have to figure out what each of these individual electric fields are and add or subtract them and determine their final direction and all that good stuff, and then you'll have another integral from this point to this point, which is just going to reduce to, once again, simple multiplication. Whatever this net electric field is, multiplied by whatever this distance is, add that to whatever you got from here, and that's your total change in voltage from R to S. And then if you want to go all the way to T, you would follow that same process. You would continue integrating. You would take this net electric field multiplied by this distance now, added on to everything we had before, and then plus the total of these 4 electric fields multiplied by that distance. And of course you have to keep track of your positives and your negatives, so that's something to watch out for. A rule of thumb to keep in mind is just figure out the direction of your net electric field in each region. And note that if you are moving against the electric field, your voltage should be increasing. If you are moving with the electric field, then your voltage should be decreasing. And by increasing or decreasing, let's define those terms. Increasing means becoming less negative or more positive, and decreasing means, well, the opposite, becoming less positive or more negative if it's already negative to begin with. So that's everything for you to keep in mind, but that is where I will have to end things for today. And I'm not sure whether or not I'm actually going to follow through on what I said. I think 2 weeks ago I might actually push back the schedule by yet another half hour for these office hours, because I mean, I started a couple minutes late tonight, and I feel like that's going to be a recurring situation, so keep an eye on the schedule on Twitch, and if you see that it's been changed, you won't be surprised if you show up half an hour too early. I still haven't decided yet, but I might decide over the week whether or not to push it back half an hour. At this point, it feels inevitable. It's just a matter of when, not if, but we'll see. I'll try to stick to this time for one more week, and if I feel like it's still not working, we'll push it back another half hour. Anyway, hopefully that's been helpful. Take care, and I'll see you next week.